Hey everyone, welcome back to Calculus videos. At this point in the semester, we're really going to be moving into the second kind of big chunk of calculus. So in first semester and for the last couple of weeks, we've been really focused on derivatives and their applications. And now moving forward, we're going to be looking at something we call integrals. And so in this video, we're first just going to do a quick recap of what we know about derivatives, and then we're going to move forward and see how this is going to relate to the new material, which will be integrals. So the first part, what we already know. So we actually know a lot about derivatives, but very basically, we know the derivative is the slope of a tangent line. We know that the derivative is also the slope of a curve at a specific point. And we know it's the instantaneous rate of change. And so far we've used derivatives to help us find a lot of things, but specifically we know that if we take the derivative of a position function, we're going to get velocity. And if we take the derivative of the velocity function, that's going to give us acceleration. So now, as we start to move forward here with integrals, what we're really going to learn to do is how to go backwards. So in other words, if I'm given the velocity function, we're going to figure out how we get position from that. And similarly, if we're given acceleration, we're going to figure out how we get velocity. And integrals are going to help us to do that. So let's talk a little more about this word I've been using, so this idea of an integral. Okay, and so what an integral is, it's a name we give to the operation that allows us to find the area between a curve and the x-axis. So integrals are going to give us areas. So we're focused on the area between the curve and the x-axis. And the notation we're going to use for that is this symbol here. That's going to be our symbol for an integral, and we'll talk a lot more about that as we move through the chapter. Now, when we work with integrals, areas that are above the x-axis, so I'm going to use a different color, areas that are above the x-axis are considered positive. So if I look at my diagram over here, I can see if I'm considering the area in between a curve and the x-axis, here I have a portion that's above the x-axis, and so that area is going to be positive. And then any areas that are below the x-axis are considered negative. So here the area trapped between that curve and the x-axis falls below the x-axis, and so that's going to be considered a negative area. Okay, so now just a little note here, and we're going to get into this a lot more later, but just a note, so it says, just like finding slopes was easy when the function was a straight line, computing integrals is easy when we have straight lines. So we're just going to be using geometric formulas. And we won't focus so much on this today, but probably in a couple of videos from here. So obviously, if we have curves bounded by straight lines, those areas are going to be really easy to calculate. In this case, we'd just be finding the area of this rectangle, which is obviously a very straightforward thing to do. Now, the challenge is going to come in, obviously, when we have curves, which are much more realistic in the situations we'll be looking at, and so we'll have to deal with how to find the areas between those curves and the x-axis. So, the focus for today is going to be, well, how do we estimate the areas under these curves? So in a little bit, we'll learn how to do this exactly, but really everything we're going to be doing in this video and in the next video is figuring out methods for estimating this area, since we don't have a method for doing it exactly yet. And so one way we can estimate the area under a curve is to use rectangles. And that's what we'll focus on for the rest of today. So when we can't use geometry formulas to find the area under a curve, so for example, I don't have any geometric figure that would fit this that I know the area of, so we're going to have to estimate. So we're going to choose to divide the area into rectangles. Then we're going to find the area of each rectangle and add them together to estimate the total area between that curve and the x-axis. And so here's what it's going to look like. We're going to have an interval that we're going to be estimating the area under. And so we're always going to be estimating the area over some interval from A to B. So if I look at my picture here, I can see my interval is going to be from 0 to 2. Now, for our case, we'll always be told in our problems how many rectangles we're going to use, but in our case, let's just say that we were doing 4 rectangles. So now, to find the base of each rectangle, we're just going to call that base generically delta x. But in our case, if I were to draw this, I know our delta x is basically we're going to be taking the length of that interval. So I'm going to take b minus a, or 2 minus 0, and I'm going to divide it by the number of rectangles. So divide by 4. So I would get 2/4 or 1/2. So that would tell me the base of my rectangle is going to be 1/2. Now, the height of each rectangle is just going to be determined by that function value. So the height is going to be determined by f of x. So just as an example here, I'm going to draw in one rectangle, and we'll talk in more detail about how I'm deciding to draw the rectangle where I am. But I'm going to draw a rectangle right here. And so when we talk about the base, we're talking about this distance here, which I said was delta x. And we can see in our picture that that's 1/2. And then the height of our rectangle is going to be this value here. So in this case, that height is going to be f of 0.5. That's going to give us the height of our rectangle. So now the area we know is length times width, so we're really going to be multiplying our delta x times f of x. So the base of that rectangle times the height, which is determined by the function value. So now, I said I drew in one of these rectangles, and now we're going to talk about how we determine where to draw those rectangles. And so we have 3 ways of doing this. So the first type we call a right Riemann sum, or a right rectangular approximation. So I'm going to call this RRAM because we'll refer to that quite a bit. And what that means, it's a right rectangular approximation method. Sorry to squeeze that in there. So right rectangular approximation method. And my pen is running out. And so here's what that means. Let's say I have 3 intervals. So I'm going to have 3 rectangles. And let's say my interval is from 0 to 3. So I know I have 3 intervals. I have an interval from 0 to 1, from 1 to 2, and from 2 to 3. And if I'm doing a right rectangular approximation or a right Riemann sum, we kind of use those synonymously, it means to determine the height of my rectangle, I'm going to use that right endpoint. So graphically, if I'm looking on the interval from 0 to 1, to find my height, I'm going to go from 1 up to the function value, and that's going to determine the height of the rectangle over that interval. Again, from 1 to 2, I'm going to use my right endpoint at 2. I'm going to go up to the function, and that determines the height. So again, that determines the height of my rectangle over that same interval. And I'll do the same thing at 3. I go up to the function, and that determines my height over that whole interval. On the other hand, I can do the same thing with the left Riemann sum. In this case, we call this LRAM, so our left rectangular approximation. Now, I'm going to start with the same scenario. So I'm going from 0 to 3. I'm going to make 3 rectangles. And so obviously if I have my intervals from 0 to 3, I'm dividing it into 3 rectangles. The base of each one is going to be 1 again. So 0 to 1, 1 to 2, and 2 to 3. But now when I draw in my rectangles, since it's a left approximation, I'm going to use the left endpoint to determine the height of my rectangle. So now I use 0, I find that height, and that's what I use to draw in my rectangle. Over the interval from 1 to 2, I find f of 1, and that's the height of my rectangle. Again, over the interval from 2 to 3, draw up to the function and use that as the height of my rectangle. So you can see these approximations differ. In this case, when I used RRAM, obviously these rectangles, I had a lot of area over the curve. So in this case, with this particular curve, RRAM happened to be an overestimate. Now when I look at LRAM, you can see I don't quite fill in all that area under the curve, so now I have an underestimate. So our last approximation method here is a midpoint sum. And so again, I have interval from 0 to 3. I'm going to do 3 rectangles. So I still have my same intervals from 0 to 1, 1 to 2, and 2 to 3. But now I'm going to use the midpoint of each interval to determine the height of my rectangle. So between 0 and 1, I would go to a half, go up to my curve, and that is the value that's going to determine the height. So it's kind of hard to see on my first interval. Let's look what happens from 1 to 2. So at 1.5, I'm going to go up. That's going to determine the height of my rectangle. So I'm going to go over. And so you can see this is kind of in between the right and left sum, because now I have portions that are under the curve and portions that are over the curve. So now between 2 and 3, one last time, I'm going to use that midpoint to find the height of the rectangle over that entire interval. So those are our 3 methods for summing or for estimating that area using rectangles. Now, the next section is really going to talk about some vocabulary that I've already been using, but it's worth talking about again here. So the subinterval. Again, a subinterval, just tells us how big to make the base of our rectangle. So that's what we're really talking about when we're talking about, we symbolize the length, so the length of each subinterval. That's what we're talking about with our delta x. So in this case, when I had 3 subintervals, the length of each subinterval is 1. So our delta x would have been 1. Now, I'm also going to put delta t here. When we start talking about applications dealing with position and velocity, our independent variable might be time. So we can see how the number of subintervals that we use will change our approximation. So let's say in this case, in my first case, I'm going to say delta t is equal to 1. So in other words, I'm using the interval from 0 to 3. My number of subintervals is 3. So then delta t is just going to be the length of my interval, 3 minus 0, over the number of subintervals, which is going to give me a length of 1. So I'm just going to illustrate this. We'll go with RRAM just for the sake of our illustration. So if the length of the subinterval is 1 and I'm using right endpoints, again, I'm going to go up to my function and that's the height of my rectangle. For my second interval, I'm using the right endpoint up to the function and over, and same thing for 3 and over to make my rectangle. Now, when I do 6 intervals, my delta t, I still have the interval from 3 to 0, but now my number of subintervals is 6. So the length is just going to be 1/2 in this case. So now I'm going to have a subinterval, so I'm going to be making rectangles at every half. Still using RRAM, so at 0 to 1/2, I'm going to draw 1 over. At 1, I go up to the function, draw it over, and I'm going to do the same thing. So now I'm taking the same interval, just dividing it into more rectangles. And the idea is ultimately that the more rectangles we use, the closer our approximation becomes. Okay, so now that we know kind of how these rectangular approximations work, we're going to learn how to actually calculate or estimate some areas using these functions. And the first thing we're going to do is actually use our calculator to help us do this. So you'll be getting a function, or excuse me, a program from your calculator that can actually compute these estimates if it's given a function. So here's an idea, or here's an example of how this works. So we have a particle that starts at x equals 0 and moves along the x-axis with velocity v of t equals t squared for time greater than or equal to 0. And we want to know where the particle is at t equals 3. So we know, we said this integral is going to help us go backwards from velocity to position. So that area under this curve between 0 and 3, the area is really what's going to give us the position. So if we could estimate that area, we could estimate the particle's position. So the first thing I'm going to do is sketch a curve for this function. So it's t squared, an easy one to work with. So I'm going to plot some points here. Okay, and just sketch in this curve here. Sorry, that's a little rough. But there we go. Okay, and so now what I'm interested in, again, if I want to know where the particle is at time equals 3, I'm interested in the area between the curve and the x-axis over the interval from 0 to 3. If I could figure out that area, then I would know the object's position. So we're going to have our calculator help us compute those areas using this rectangular approximation. And we're going to use it with the program called RAM. Now, a few things I want to make a note of. The first is that to use RAM, the function that you're using must be entered into y equals. So in other words, this program is going to pull from your y equals. So if you have some function other than what you're working with, it's going to give you an incorrect answer. So if I'm working with this problem, I'm going to pull up my programs and I'm going to select RAM. Oh, excuse me, actually I'm going to go to y equals and make sure this function is in y equals. So I'm going to put in my x squared. Now I'm going to go to RAM, and you'll see when you hit enter, it's going to ask you for a few things. So A is going to be the left endpoint of your interval, and I'll write this down in a second. In our case, we're starting at 0, so our A is 0. B is going to be the right endpoint of our interval. So for us, that's going to be 3, because I want to know where it's at time equals 3. Now, the next thing it's going to ask you for is the number of subintervals. So we're going to use this to fill in this table. So we're going to start with 6. So when we hit enter, it's going to calculate those areas for us. So it gives us a left, a midpoint, and a right. So left RAM, LRAM, is 6.875. My midpoint is 8.9375, and RRAM is 11.375. Now, I'm not going to fill in this entire table. I'll only do 2 more. So let's go ahead and see what happens if we do it now. Same interval from 0 to 3, but now we're going to do 12 subintervals. So now the idea is that as we do more rectangles, we should be getting a better and better approximation. And then 10.15625. And notice MRAM is always going to be in between LRAM and RRAM. And so I'm going to do one more here. I'm just going to jump to 100. So I'm going to do my programs, RAM, still from 0 to 3, and with 100 subintervals. And now sometimes it takes a while for it to think. While it's doing that, I'm going to make a note that in our program, A is the left endpoint of our interval, and B is the right endpoint. And so now if I go back here, it's kind of come up with what it was working on. I get the left is 8.86545, midpoint 999,775, and then for my right, 9.13545. Whoops, I'm sorry. These numbers should all be down here. So again, as we get larger and larger, much more precise. Now we are limited. If you put in an n that's too great, it's going to take forever for your calculator to come up with that approximation. So I usually stick somewhere around 100 subintervals. So now, a few notes that we already kind of mentioned. MRAM is always going to be between LRAM and RRAM. And as n gets larger, all 3 values get closer together. So you can see the difference between LRAM and RRAM is going to narrow as we have more and more subintervals. And so in general, when asked to use RRAM to estimate, we're going to keep increasing n until the first, I would say 2 or 3. Ideally 3, but sometimes it's going to take too long to get to that third place. So 2 or 3 digits after the decimal point are the same for LRAM, RRAM, and MRAM. Then we know we have a really good estimate. So the next 2 questions are just quick calculator questions using our program. So the first one says to estimate the area under the curve f of x equals x squared times sine of x over the interval 0, 3 using LRAM with 3 subintervals. So all that's asking you to do is plug this into your calculator. So again, remember we said the function has to be entered in y equals. So I'm going to go and make sure I've got my function in y equals. So I've got x squared times sine of x. So now I've got my function in y equals. I'm going to go back to my program. I'm going to execute RAM. I know my A is going to be 0, my left endpoint. I'll put this over here. B is the right endpoint, so that's 3. And then the subintervals is going to be 3. So if I hit enter, my question asked me for LRAM, so I'm going to use my left endpoint. So I'm going to get a value of 5.749. I'm going to go to 3 places there. Okay, now second one, again, just in making sure we can use our program and get the same values. Now I have a new function, so I'm going to go back to my y equals, and I'm going to type in my new function here. So I have 2x squared minus 12x plus 22. So now I can go to program. My interval is from 0 to 4. And I have 5 subintervals this time. And since the problem asked me for RRAM, I'm going to use my right approximation, so I have 29.12. Now obviously, because my number of subintervals are so low, these would not be very good approximations, but right now we're just learning how to use the calculator. Alright, so the next thing we need to do is learn how to do this by hand. So we're not going to be using the calculator at this point. So I think what we'll do in the interest of time, because this is already getting to be quite long, is we'll do number 3. We'll talk about doing this from a function, and then when we come back to class, we can go over the examples looking at the table. We can do those all together. So we'll just do number 3, and we might only, for the purposes of the video, I might just show you RRAM, and then we'll kind of go from there when we're back in class. So for number 3, it says estimate the area between f of x equals x squared plus 3 and the x-axis on the interval from 0 to 4 using n equals 4 subintervals. And again, I'm just going to work with RRAM for right now. So the first thing I'm going to do is actually sketch a graph. Now you won't have to do this every time, but I think while we're still kind of visualizing what's happening here, it's good to draw a graph. So I'm going to sketch. I know I'm going from 0 to 4. So let's see. So here's my x. And let's see, my y is going to go up to 19. So I'm going to go by 5s and hopefully come up with a decent sketch here. So if I plug in 1, I'm going to get a value of 4. 2 is going to give me 7. And I'm just kind of doing my best to estimate here. 3 is going to give me 12. It's maybe about here. And then this will give me 19. So I know I have, I'm just doing a piece of this parabola over this interval. So obviously this is going to continue. But I'm just worried about this piece for our purposes. So now, we know our subinterval, or our interval, excuse me, is from 0 to 4, and we're going to use 4 subintervals. So I need to figure out what the base of my rectangle is going to be. And we said that was going to come from delta x. So delta x is the length of our interval, so 4 minus 0, over the number of subintervals. So that's going to tell me the base of each rectangle is going to be 1. Now, since I'm using RRAM, I'm going to use the right endpoint of each of those intervals. Oh, I'm sorry, this is from 0 to 4, so I need to have a point here. So it's this piece here. Okay, so I'm using the right interval, or the right endpoint. So my first interval is going to be from 0 to 1. So to draw my rectangle, the right endpoint of that first interval is at 1. So I'm going to draw up and over to get the height of my rectangle. My second interval is from 1 to 2. I'm using the right endpoint to determine that height, so I go up to the function and over. Same thing for 3, and then up and over at 4. So that's graphically kind of what's happening. So we expect that we're going to have an overestimate because a lot of this area falls above the curve. So now to calculate this with RRAM, here's what I'm going to do. I'm just going to sketch out the base of each of my intervals. So I have from 0 to 1, from 1 to 2, 2 to 3, and 3 to 4. And to find the height of each rectangle, I'm going to use the right endpoint. Now remember, we said that height comes from finding the function value at that point. So my height of my first rectangle is going to be f of 1, which we know is 1 squared is 1 plus 3 is going to be 4. And I'm going to find the value for each of these right endpoints. So f of 2, I know is 7. F of 3 is going to be 12. And then f of 4 is 19. So now we said the area of each rectangle is going to be the base, which is delta x, times the function value f of x. So if I wanted to find the total area, I would add the area of each of these rectangles. So my first area, the base is 1, the height is 4. My second one, I still have a base of 1 times a height of 7. Third one, base of 1 and a height of 12. And the last one has a base of 1 and a height of 19. Now, in this case, since we have equal subintervals, you'll notice in each case that the base of the rectangle was just 1. So what you'll see me going forward is if I have equal subintervals, I'll just pull out the base once in front, basically factoring it out, and then I'm just going to add all the heights. So there's my 1. I just factored it out because it's the same height for each rectangle. I'm going to add these up, and I get an area of 42. So that's my estimate for the area between that curve and the x-axis over the interval from 0 to 4. And now I can go ahead and check that using my calculator if I'm not sure that I did it quite right. I can check that by going to y equals. I'm going to make sure I have x squared plus 3. Go to my program, which is RAM. Hit enter. My left endpoint is going to be 0, right endpoint is 4, and I have 4 subintervals. And then you can see our right approximation is 42, so we've done it correctly. So, since I've gone way over what I usually like to do for videos, we'll stop there. When we're back in class, we'll just quickly do a comparison of how this would be different if we were to use LRAM or MRAM, and then we'll look at how to compute these areas by hand if we only have a table. Thanks for hanging in there, and I'll see you in class.